Hey guys, welcome to another lecture video for Chem 115. In this video, I will introduce the concept of buffers, such as what they're composed of, why they are important for us to discuss, and the general mechanism of how buffers work. So this is the first part of several videos for buffers. The other videos that I hope you guys will watch will cover the general themes of how to tackle word problems involving buffers. So please make sure to watch them so that you can build these skills that's necessary to tackle similar problems, whether they're on a worksheet, in a lab, or on your exam. So let's get started. To introduce this topic, we're simply going to ask this question: what are buffers? And so buffers are solutions that resist a change in pH. When hydrogen ions or hydroxide ions are added to it. And so to demonstrate this definition, we're going to do some digital chemistry here. And so here we have this beaker that's filled with water. And we're going to go ahead and stick in a pH probe that's connected to this pH meter. And let's just say that the system is now at equilibrium and the pH is reading 7.00. And so what would happen to this pH if we added hydrochloric acid to it? And so as Chem 115 students, you guys should be able to calculate the pH of this. So if we know the concentration of hydrogen ions that we added, we should be able to predict the pH of the solution. But instead of quantifying it, we're going to think about the concept. And so if we add hydrochloric acid to water, we know that hydrochloric acid breaks down into H plus and Cl minus. And so here we're going to get some H pluses and Cl minus floating in this solution. And since H plus is present in that solution, it's going to increase the concentration of the hydrogen ion. And if you increase the concentration of hydrogen ion, your pH is going to be more acidic. And the only way that's going to be conveyed on the pH scale is that if we have a lower value than our initial. So let's just say that we added in HCl and it lowered it to 1.50. Okay. So this dramatic decrease in pH units lets us know that this solution is not able to resist a change in pH. And so we can go ahead and conclude that this solution is not a buffer. Okay. Now, if we were to reset this digital experiment, so to speak, okay. And so instead of us having water inside that beaker, what if we actually have a buffer solution? And we'll talk about the components of the buffer solution, but for now, we're just going to add that word in here. Okay. And so recall that a buffer resists a change in pH. And so if we add the same amount of hydrochloric acid as we added into water, the hydrochloric acid is still going to produce this H plus, and that's Cl minus. And we'll take a look at the mechanism of how a buffer actually resists a change in pH. But for now, it's okay for us to just understand that somehow this hydrogen ion is absorbed by the buffer. And so if the hydrogen ion is absorbed by the buffer, it's no longer going to be present inside that solution. And so if the hydrogen ion is no longer present, then will there be a significant change in pH? And so the answer is no. Since the concentration of hydrogen ion stayed roughly the same, okay, maybe we have slight extra, or I just, you don't know. What's going to happen is that the resulting pH is going to either stay the same, it can either stay as 7.00, or it can go down very, very slightly, so like 0.01 pH unit. However, if you guys compare the values, notice that the pH did not change by very much. And so this is how buffers resist changes in pH. So it somehow absorbs that hydrogen ion that was added. And the same idea can be applied to hydroxide. Somehow it's absorbing these two components so that the concentration of hydrogen ion and the concentration of hydroxide ion remains the same. Okay. And so now that we've discussed the definition of buffers, and we're going to go ahead and talk about the composition of buffers. So what are they composed of? So what is this magic mixture? So buffers are composed of something that we've already discussed. They're composed of a weak acid and its conjugate base. And so another way that these buffers can be composed is having a weak base and its conjugate acid. And so we're going to go ahead and take a look at a couple of examples just to see an example of a weak acid and its conjugate base and a weak base and its conjugate acid. But the main important thing for us to take away is that the presence of a weak acid and its conjugate base, or a weak base and its conjugate acid, is the prerequisite for a solution being a buffer. If it is anything outside of a weak acid and its conjugate base, or a weak base and its direct conjugate acid, it probably will not act as a buffer. All right, so let's go ahead and look at an example. One example is acetic acid and its conjugate, which is acetate. And so the chemical formula for acetic acid is HC2H3O2. There's actually others. There's other chemical formulas for acetic acid that you guys might run across. Another way that acetic acid can be presented is, let's see here, so CH3, COOH, okay, or HCH3, CO2. Okay. There's slight variations, there's other variations of acetic acid. However, whenever you guys are looking at this compound, and if you guys can count that there's 2 carbons, 3 hydrogens, and 2 oxygens, and an extra hydrogen, then that's most likely going to be acetic acid. And so what makes acetic acid an acid is because it has one ionizable hydrogen ion. And so from previous lecture videos, we know that acetic acid is not a strong acid, so this is considered a weak acid. And so if acetic acid is inside the solution, for it to be a buffer, the conjugate must also be present. And so the conjugate of acetic acid is acetate. And so to write the conjugate of acetic acid, we're simply going to ionize this hydrogen so that we get C2H3O2 with a -1 charge. And so this compound is going to represent the conjugate base of this weak acid. Now, it's not exclusive going one way. And so, for example, if we had acetate in our solution, for it to be a buffer, it must have its conjugate, which is acetic acid. In other words, if we treat acetate as our weak base, fulfilling the second part of the composition, for the second part of this rule, so to speak, so if we treat acetate as a weak base, then acetic acid becomes the conjugate acid. And so we can go ahead and treat them, backwards and forwards. And so because they're conjugates of each other, acetic acid and acetate is known as an conjugate acid-base pair. And it just really depends on how you guys are just throwing that terminology out there. So if you're saying that acetate is the weak base, then the conjugate acid is acetic acid. If acetic acid is the weak acid, then the conjugate base is going to be acetate. Okay. So we can go ahead and apply that same, actually, you know what, before we do ammonia and ammonium, I want to talk about acetate just a little bit more. And so typically in lab, when we're preparing these buffers, we just don't simply have acetate. So sometimes when we order these chemicals, acetate comes in as a solid, and for it to come in as a solid crystal, it's complex with a cation. So for example, sodium is a cation. So sometimes you guys might see in a word problem or in a label of a chemical bottle, it'll have like NaC2H3O2. Okay, so this is just simply sodium acetate. And so from the first semester of general chemistry and from a previous lecture video, I've mentioned that sodium, since it's a group 1A metal, it's under the perspective of the first semester of general chemistry, sodium is a spectator ion, so just does nothing in solution. And so what you technically have is acetate. We also know that the sodium does not change the pH of the solution, simply because it follows under Rule 1 to justify it, right? So group 1A and group 2A ions, they do not, except for beryllium, do not affect the pH of the solution. And so when you guys are reading like NaC2H3O2 in a word problem, don't freak out. Just recognize that sodium can be extracted or taken out completely from that chemical formula. And the only thing that you have left over is acetate. And so it doesn't have to be sodium. It can be like potassium or lithium or some other group 1A element. Okay. So let's go ahead and talk about ammonia and ammonium. And so ammonia is NH3. And so if you were to draw the Lewis structure of NH3, we would have 3 hydrogens that are covalently bonded to nitrogen, and there would be a lone pair. And so this lone pair would enable ammonia to act as a Lewis base or a Bronsted base. And so ammonia is considered a weak base. And so therefore ammonium, or NH4 plus, is going to be the conjugate acid. So this is the conjugate acid of ammonia, which is considered a weak base. And so if we wanted to kind of go in reverse, we can say that NH4 plus is the weak acid, and therefore its conjugate, which is ammonia, would be the conjugate base. Okay, and so once again we can go forwards and backwards with this train of thought. The main idea is that once you have a weak acid and its conjugate, or a weak base and its conjugate inside a solution, then you guys have a buffer. And so very similar to acetate, if we wanted, to prepare an ammonia ammonium buffer solution, sometimes when we order this, ammonia is complexed with, for example, a halide such as chloride, so NH4Cl, right? So if you guys were to see this in a word problem or on a label of a chemical bottle, we know that chloride does not affect the pH of the solution, and therefore we could ignore it and just focus on NH4 as the active ingredient, so to speak, that will affect the pH of the solution. Okay. And once again, if you don't know why chloride doesn't affect the pH of the solution, I encourage you to watch my lecture video on how to determine if ions of an ionic salt affects the pH of the solution. All right. So now that we have an idea of buffers, what the composition of buffers are, weak acid, conjugate base, weak base, conjugate acid, I want to address a couple of common questions that I get from students. And so, how do we know if a substance is a weak acid or a base, right? So when I was doing this, I just basically told you that this is a weak acid or this is a weak base. So how do we know if a substance is a weak acid or a weak base? And so I want to go ahead and bring up this list. Once again, I've brought this list up several times in other lecture videos. So these are the common strong acids and the common strong bases that you guys should really know, that you guys should memorize. And so basically, if a compound is presented to you, and it's not on this list of common strong acids and common strong bases, then you can kind of conclude with a degree of certainty that the compound is going to be weak. So if it's not on this list, it's a weak acid or a weak base. The only exception to that rule is if the Ka or Kb values is given or known, then you can go ahead and look at the Ka value and determine if the compound is a weak acid or a strong acid. So for example, if your acid ionization constant is far, far greater than 1, so for example, I don't know, 1.23 times 10 to the positive 4 or something like that, so that's a large number, then we can go ahead and conclude that this substance is a strong acid. And so if your Ka is far, far less than 1, so we're going to go ahead and use that same number. We're going to flip the sign. I'm cheating, I know. And so here in this case, if our acid ionization constant for this random example is 1.23 times 10 to the negative 4, since it's far, far less than 1, this is going to be considered a weak acid. Okay. So you have two ways to determine if a substance is a weak acid or a weak base. If no Ka values is given to you, or if you don't have access to them, then you guys can just use this list of common strong acids and common strong bases. So basically, if it's not on this list, it's going to be a weak acid or weak base. Now, if the Ka or Kb values are actually given to you, then you need to use those Ka values or Kb values to determine if it's a strong acid, weak acid, strong base, weak base. Okay. All right, so the second question that I get from students is, how do we know that the compounds presented to me in the problem are conjugates of each other? Okay. And so I'm actually going to erase this here. And so what if in the problem, I think I just kind of gave it away, but that's okay. All right, so let's go ahead and look at these two examples to determine if they're conjugates of each other. So looking at this problem on the left, HF and NAF, there's a couple things that we need to kind of check to determine whether or not they're conjugates of each other. The first thing, the first item that we're going to do is, check to see if the anion is the same. Okay. I'll put in this guy here. And so looking at both of my examples, I have F and F. Those are both anions. And I have CO3 and CO3. Okay. And so it turns out that both of them kind of fulfill this prerequisite. Both of the anions are the same. And so the second item that we need to check is determine whether or not the number of hydrogen ions is off by 1. Okay. So if I look at this example on the left, HF has 1 hydrogen ion. And if you guys compare that to the product, notice that there's no hydrogen ion. And so it looks like as we go from the left to that of the right, we're losing a hydrogen ion. Specifically, we are losing 1 hydrogen ion. Now, if you go from the right to the left, the product to the reactant, so we're looking at the reverse reaction, notice that we're gaining a hydrogen ion. And so let's go ahead and talk about this sodium, right? Once again, remember that sodium is a group 1A element, and according to your solubility rules, sodium, any compound that's with sodium, when you place it in solution, it'll dissociate from each other. And so really what you have here is just F minus, or is just F or F minus. Okay, so I'll just write that over here. So NaF will decompose to Na plus and F minus. And so since sodium is a spectator ion, we're going to go ahead and just ignore that. And really the only item that we have on the right-hand side that's related to HF is F minus. Okay. And so between F minus and HF, they're off by exactly one hydrogen ion. Okay. And so it looks like since this example, this HF to F minus, checks off both prerequisites, then we would say that HF and F minus, or NAF, are conjugates of each other. So they are conjugate acid-base pairs. Oops. Okay. And so let's go ahead and take a look at, I'm going to go ahead and erase this guy real quick. Okay. Let's go ahead and check out that second example. And so we already know that the anion is going to be the same. And so what we need to do next is check to see if hydrogen ion is off by 1 between both of these compounds. And so since we're dealing with sodium once again, we're going to go ahead and ignore this. And so we can rewrite this as H2CO3 and then CO3 2 minus. So remember, sodium does not affect the pH of the solution because it's a group 1A element. And according to first semester general chemistry, you know that sodium is a spectator ion. And so therefore we can just go ahead and completely ignore it. And we know that's just in the background floating, doing nothing. And so here in this case, what we just have is carbonic acid and carbonate. Now, if you look in the forward direction, for me to go from carbonic acid to carbonate, I would have to lose 2 hydrogen ions. And if I go in the reverse direction, for me to go from carbonate to carbonic acid, I would have to gain 2 hydrogen ions. And so since the number of hydrogen ions gained or lost is not 1, this example does not fulfill the second prerequisite. So therefore, H2CO3 and CO3 2 minus are not conjugate acid base pairs. Okay. And so since they're not conjugate acid base pairs, then then they cannot act as a buffer. And so something else would have to happen for these two substances to act as a buffer. Okay. All right. So hopefully by going through those 2 common questions, you guys understand how to identify if the substances that's presented to you are conjugate acid base pairs, and if they're weak acids, weak bases, or strong acids, strong bases. So the reason why I went through those 2 questions is because you guys need to be able to determine if each of these following compounds, or each pair of compounds, can act as a buffer in solution. And so I'm just going to go ahead and put off to the side some notes that we can utilize, some guidelines. And so 1, they must be weak acid, and its conjugate base must be, or it must be a weak base and conjugate acid. So long story short, we need to confirm whether or not they're weak acids or weak base. And so if we confirmed that they are weak acid, weak bases, then the next thing that we're going to ask ourselves is, are they conjugates of each other? Okay. And we're going to go ahead and use these 2 prerequisites. Oh no, what happened? Okay. And so we're going to go ahead and use these 2 prerequisites we're going to check to see if the anion is the same, and if we're also going to check that the number of hydrogens between the two compounds is only off by 1. So are anions the same? And the change in hydrogen ions, is that equal to 1? Okay. So if we're able to check every single one of these items off, then that will help us determine if the compounds in that pair can act as a buffer. So let's go ahead and look at the first. So here we have bicarbonate and we have carbonic acid. So can these two act as a buffer? Let's go through the list. First and foremost, we need to determine if they are weak acids or weak bases. How do we do that? Well, we're going to look at our list. And so notice that we're looking for items that have a carbonate. And so if you look through this list of common strong acids, common strong bases, you will not see a carbonate. Okay. We see a chlorate, but a ClO3 is not the same as CO3. So since it's not on that list and the Ka values was not given to us, then we can go ahead and just rely on that list and conclude that H2CO3 is a weak acid. Okay. And you can also do it with HCO3 minus. If it has that minus charge, it's indicating that it's a base. If you look at our base, common strong bases, we don't see HCO3 minus. And so we know that this is a weak base. Okay, so it looks like this guy got checked off, and so we're moving on to number 2. Are they conjugates of each other? And to determine if they're conjugates, the anions must be the same, and the change in the concentration of hydrogen ions just has to be 1. And so I'm going to look at my anion, and we both have carbonates, and so therefore it checks off this part. And we need to see if the number of hydrogen ions is just off by 1. And so this is 1 hydrogen, and then here we have 2 hydrogens. And so the difference between these two is 1. Okay. And so since we were able to check off number 1 and number 2, then we can go ahead and conclude that both of these substances, when they're placed together in a solution, can act as a buffer. Okay. All right, so I'm going to go ahead and reset my check marks because I need to go through another example. All right, so if we have HCl and Cl minus, we're going to go ahead and determine whether or not these substances, if they're both placed in a solution, will produce a buffer. Okay. So let's go ahead and look at prerequisite number 1. We need to determine if they are weak acids and weak bases. Okay. So the first item that I see is HCl. So I'm going to scroll all the way up, and boom, I see HCl as a common strong acid. So since HCl is a strong acid, it does not fulfill the first prerequisite, if you will. And if it doesn't fulfill the first prerequisite, there's no point in doing the rest, right? If it's a strong acid, it's not a weak acid. And so therefore, these substances, when put in a solution, cannot act as a buffer. Okay. All right. And so I want you guys, hopefully you guys are getting the pattern. I want you guys to go ahead and pause this video, and I'll give you guys, I'll do some silent pause on my own. I want you guys to kind of go through this list and determine if any of these can act as a buffer. So feel free to pause the video, just write this down, and maybe rewind this video just a little bit so you guys can, I'll just flash it here. So these are like the prerequisites. Okay. All right. All right. So hopefully you guys were able to identify which of these three can act as a buffer and which of these three cannot act as a buffer. So let's go through the answers. And so looking at this next example, we have H3PO4. And so we're going to go ahead and ask ourselves, is H3PO4 a weak acid? And so if you notice, we won't find any phosphates over here, not in the common strong bases, not in the common strong acids. And so therefore, without any other information, we can go ahead and safely conclude that this is a weak acid. Okay. And so let's go ahead and look at the second component. So is this a weak base? Okay. And if you notice, let's see here, Cl, actually, you know what? I won't even get to that point. It's probably going to throw your logic off. So let's just keep it as is. Let's just say that, hey, we identified that H3PO4 is a weak acid. Okay, and then we're going to go ahead and move on. And so if we're looking at rule number 2, are they conjugates of each other? The first part to this, are their anions the same? And so if you look at the anions, phosphate and chloride are not the same. And so if they're not the same, then we're just going to put an X. And once we have one X, we do not need to continue further. This is already failed one of these questions. And so if it fails one of these questions, then automatically we can say that this pair of compounds will not, cannot act as a buffer. All right, so just to kind of speed things along, I'm going to go ahead and just highlight some key points. So here we have H3PO4, very similar to what we did in the previous example. We concluded that it's a weak acid. And if you look at the if you look at H2PO4, notice that they have the same anion. And the last thing that we need to check is the number of hydrogen ions, the difference in the number of hydrogens between them. And the difference between 3 and 2 is 1. Now, if you looked at 2 and 3, you might say, oh, hey, that's -1. So just take the absolute value. And so the difference between those two compounds in terms of the number of hydrogen ions must be just 1 unit. And so since it fulfills all 3 of this, it's a weak acid, it's an anion, anions are the same, and the difference of hydrogens is 1, then you can go ahead and say, you can go ahead and conclude that these two compounds can act as a buffer. And so last but not least, we have HNO3 and LiNO3. And so I noticed that they both have the same anion, so it could be, right? And also, we know that lithium is a spectator ion, and so really what we have is just HNO3 and NO3 minus. And if you look at the difference in the number of hydrogens, it's off by 1. So really, the next example checks off number 2, right? The anions are the same, and the difference in the hydrogens is off by 1. And so we need to check if HNO3 is a weak acid or a strong acid. And so if you look at the list of common strong acids, boom, HNO3 is right on that list. And so therefore, we can conclude, since it fails this first prerequisite, so HNO3 is a strong acid, then we can conclude that these two compounds, when placed in a solution, cannot act as a buffer. Okay, so hopefully after going through this exercise, you guys are able to determine what are conjugate acids and conjugate bases. You guys should be able to determine which of them are weak bases, weak acids, strong bases, strong acids. So it really does pay off knowing or memorizing this list, especially when it comes to these qualitative concepts. So please don't be afraid to memorize this list. There's patterns to it, and I'm going to go ahead and leave you to understand that pattern. So that way you guys can kind of internalize it on your own. Okay? So think about like families, halogens, groups, etc., etc. Okay. All right. So now that we understand how to determine if the substances given to us is going to act as a buffer or not, the next thing I want to talk about is, why are buffers so important? And so buffers, they serve a strong purpose, strong role in both industry and biology. So for example, in a chemistry or biochemistry lab, you guys can use a buffer to stabilize a cell culture or to ensure that a side reaction does not occur. And for example, in organic chemistry. However, what I want to discuss is the importance of buffers through a biochemical perspective. So something that's related to biology. And so in an organism, it doesn't really matter if it's like a human or a bacteria or a rat. There's a lot of catabolic and anabolic processes that occur inside that organism. And so these processes can produce hydrogen ions and hydroxide ions. And so one can imagine that if, left unchecked, the excess hydrogen ions and hydroxide ions can have some biochemical effect on, for example, proteins, which is a class of macromolecules. And so for me as a protein chemist, I know that if these hydrogen ions and hydroxide ions are left unregulated, then the excess hydrogen ions and hydroxide ions can affect the secondary, tertiary, and quaternary structures of proteins. And so for example, if this is my protein, right? Each protein has a specific three-dimensional structure to them that allows them to function, that allows them to fulfill their role as a catalyst. And so if you have a whole bunch of H pluses, what's going to happen is that these charged species is going to interact with this protein, and the amino acids that make up the protein, depending on their side chain, can probably interact with H pluses, therefore slightly changing its structure, whether it be secondary, tertiary, quaternary. So it can interfere with the intermolecular forces that's like naturally present to keep the three-dimensional fold of that protein. And so, with the addition of hydrogen ions or hydroxide ions, your protein can denature or unfold. And if your protein is denatured, then it can no longer act as a catalyst in that biochemical process. And then there's going to be some negative downward effects to it. And so the main purpose of a buffer in a biological system is to really absorb that excess hydrogen ions and that hydroxide ions that's produced naturally from catabolic and anabolic processes. And so overall, it allows the pH to be maintained. And the maintenance of that pH will ensure that the three-dimensional fold, the three-dimensional structure of key proteins will remain intact, such that it's not going to unravel, and it's just in the right conformation for substrates to go inside the protein, and a catalyst will be some type of reaction will occur. I'm trying to not throw out a lot of details. All right, cool. And so in the human body, there's a lot of buffer systems. And so, for example, you can have a phosphate buffer system or an ammonium buffer system. We've seen what phosphates look like and ammonium look like in the earlier part of this lecture, so we can think about what their conjugates are to create that buffer. And so the importance of the phosphate buffer and ammonium buffer just kind of differ depending on where it's located inside the cell or organ. The buffer system that I want to highlight in this lecture is a carbonic acid and bicarbonate system. And it's most predominant in our blood. And so the main purpose of the carbonic acid bicarbonate buffer system is to maintain the blood pH to about a 7.4. Okay. And so let's go ahead and look at the chemistry of this buffer system. And so carbonic acid has a chemical formula of H2CO3. And so since it has two hydrogens, this is a diprotic acid. And so since it's a diprotic acid, it has two ionization constants, Ka1 and Ka2. Now, if you guys look at Ka2, the second ionization of this hydrogen, so this hydrogen is going to be ionized. If you look at that exponent, notice that it is times 10 to the negative 11. And so this is telling us that a very, 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 very small fraction of hydrogen carbonate or bicarbonate at equilibrium will actually ionize and produce H plus and carbonate. This times 10 to the negative 11 lets us know that the reactant in the forward direction is going to be more present in the solution. In other words, the bicarbonate is going to stay as is. Most of the bicarbonate in that solution will not ionize. All right, so the main point of that is to highlight that this is the main buffer system that's occurring in our blood. And so, yes, there is a second ionization of that bicarbonate, but since its second ionization is times 10 to the negative 11 compared to times 10 to the negative 7, we would say that this ionization is not significant. It happens, but it's not significant. And so when we're talking about the carbonic acid bicarbonate buffer system in blood, we're only thinking about what's happening in this yellow box that I circled. And so this carbonic acid and bicarbonate, the weak acid, is going to be carbonic acid. And the bicarbonate is going to be our conjugate base, if we're looking at it in the forward direction. Now, if we're looking at it in the reverse direction, bicarbonate would be our weak base, and carbonic acid would be our conjugate acid. And so what I want to do is kind of explore what would happen when external factors affect the equilibrium of the system. So I'm kind of piggybacking off of what we learned in previous chapter, so Le Chatelier's principle. So for us to understand the effects, the biological and symptomatic effects of a change in pH due to disturbances caused by external factors, we need to understand a different equilibrium. It's not too different. I'm just adding on one more item. And so in our respiring cells, so this is cells that produce CO2, such as like our muscle cells, well, basically almost every single cell is a respiring cell. So glucose is converted into biological energy, and it utilizes oxygen, and that oxygen, once it's consumed, one of the byproducts in that oxidative phosphorylation and Krebs cycle process, actually more specifically the Krebs cycle process, is CO2. And so imagine that this respiring cell is producing CO2, and this CO2 is going to diffuse into the red blood cell. So I'll put in red blood cell, RBC. And so it turns out, actually, you know what, the whole thing is going to, oops. So let's just say that this whole thing is going to be in the red blood cell. So the respiring cell is going to produce CO2. And so in the red blood cell, or RBC, there's going to be this protein called carbonic anhydrase that's going to take the CO2 that diffused inside the red blood cell, and it's going to react. It's going to take that CO2, going to take a water molecule, put them together to form carbonic acid. And since the Ka, once carbonic acid is made, the natural function of an acid will occur, and such that a small population of H2CO3 is going to break down and produce H plus and bicarbonate. So this is our buffer system. And so what I want to do is kind of explore what would happen if external factors, such as drugs or other external factors, will affect this equilibrium. And so let's just say that you have some type of airway obstruction. That airway obstruction can be caused by pneumonia, COPD, and the list kind of goes on. And so if you have an airway obstruction, oops. What's going to happen is that CO2 is going to be retained. So there's going to be an increased retention in CO2. In chemistry terms, what happens is that there's going to be an increase in CO2 concentration if the airway is obstructed. And so if there's a increase in CO2, it's going to shift the equilibrium according to Le Chatelier's principle, such that the equilibrium will shift to the right. And since the equilibrium is shifting to the right, it's producing more carbonic acid. And if you produce more carbonic acid, again, we have another shift to the right, producing an increase in the concentration of H+. And so, long story short, the pH of our blood is going to be more acidic if we have some type of airway obstruction not allowing us to exhale that CO2. And so this is known as respiratory acidosis. So there is another terminology, it's called metabolic acidosis, but metabolic acidosis is caused by things such as like diabetes, shock, renal failure, et cetera, et cetera. And so what I'm focused on right now is respiratory acidosis. And so for respiratory acidosis, it's marked by an increase in the level of CO2 in our blood. And according to Le Chatelier's principle, if we have an increase in the concentration of CO2, it's to counteract that increase, what's going to happen is that it's going to try to consume the excess CO2. And if you consume excess CO2, then you're going to be producing more HCO3. And if you produce more carbonic acid, you have a higher population of that H2CO3 that's going to dissociate and produce hydrogen ions. And so overall, you have an increase in hydrogen ions. And so some symptoms, and so we would call this hypoxic. So this is a hypoxic environment, so hypoxia. And so some symptoms are not, I wouldn't say symptoms. So for example, if this were to occur and if it were to occur for a prolonged period of time and it's not treated in some form or manner, things such as like headache, muscle weakness, disorientation, dizziness, drowsiness will be experienced by that individual. And so we can also take a look at the opposite direction. So instead of the airway being obstructed, so I'm going to reset some of this stuff. So instead of the airway being obstructed, we're going to have a loss of CO2 from our lungs. And so this could be caused by hyperventilation. And hyperventilation, typically if you experience prolonged anxiety or fear, you tend to breathe out more than you breathe in. And so if you are constantly losing CO2, it's going to throw off this balance of pH or concentration of hydrogen ion. And so if you are exhaling more CO2 than what your body normally does, what happens is that you decrease the concentration of CO2. And so since everything here is kind of connected, to compensate for the CO2 that's lost, the excess CO2 that's lost in the lungs, this bicarbonate is going to react, or it's going to consume the hydrogen ions that's present in the solution to form carbonic acid. So that carbonic acid, through carbonic anhydrase, can replenish the CO2 that's lost. Okay. And so overall, we have a shift in our equilibrium such that we're shifting the equilibrium to the left. Okay. And so if you think back at Le Chatelier's principle, if we consume our reactant to compensate for the reactant that's lost, we have to break down our products, right? So we have to consume products to produce reactants that were lost. And so this is a scenario in which you would be diagnosed as having respiratory alkalosis. Okay, so everything is happening inside the lungs. Respiratory alkalosis. And once again, this is, triggered by a loss of CO2 in the lungs, whether through hyperventilation, or, for example, if you are on a mechanical system, if an individual is reliant on a mechanical system to inflate and deflate their lungs, if there's a failure in that system, then it could lead to more CO2 being extracted out of that individual and not enough oxygen being put in. And so respiratory alkalosis is loss of CO2 in the lungs defines respiratory alkalosis. And so some things that can be observed, so in other words, an individual can have a seizure, your muscles can cramp, oops, okay, your heart rate is not normal, you get like numbness or tingling, and so all of these symptoms just arise because your blood pH is thrown off due to a loss in one of the components in this equilibrium. And so it kind of shows you how important it is for our blood pH to be maintained at 7.4. Any pH value above it or below it that's caused by some type of like external influence, whether it be hyperventilation or hypoventilation, or airway obstruction, I apologize, is going to result in some type of, it's going to manifest some symptoms, such as seizure, muscle cramping, headache, drowsiness, dizziness, disorientation, and the list kind of continues. Okay, so hopefully that kind of demonstrates the importance of our buffers. So the next thing that I want to cover is how do buffers work. Okay. So the very beginning of this lecture, I showed you that if you add, like acid inside a buffer solution, the pH doesn't really change. And so what we want to address is how that mechanism actually works. And so how does it absorb that hydrogen ion? How does it absorb that hydroxide ion so that the pH does not change significantly? And so before I start this section, I want to note that the concentration of hydrogen ion and the concentration of the hydroxide ion, any fluctuations in the actual concentration will change the pH or the pOH. Okay, so if there's a change in the actual value or the actual number of, So if there's a change in the concentration of hydrogen ion, or if there's a change in the concentration of hydroxide ion, then there's going to be a change in pH or pOH. Okay, so that triangle is representing change. So I just want to throw that out there as a background info, so that when we go through this mechanism, you hopefully those 2 points connect. And so let's just say that we have HA. HA is going to be our weak acid in this scenario. And so an example of a weak acid is that carbonic acid in that carbonate buffer system, or bicarbonate buffer system. And so our A- inside this solution is going to be the conjugate base. An example of a conjugate base would be that bicarbonate. So imagine that you have this buffer system inside your beaker, and let's just say that you put in some strong acid, such as hydrobromic acid. And so when you put hydrobromic acid inside this solution, that HBr is not going to retain as HBr. In other words, in solution, it's going to separate into H plus and Br minus. And so what you have here is just H plus and Br minus, okay, floating in solution. Now I'm going to go ahead and, well, I'll just keep the Br minus in there. And so we have this H plus that's floating in solution. If you think about the chemistry of acids and bases, H plus is an acid. And so do you think that H plus is going to just float by itself and not react with another substance? And so the answer to that is no. And so this H plus can bump to HA. It can bump to Br minus, and it can kind of like bump to this A minus. And so from our first reaction, we know that when we have HBr, it's going to separate into H plus and Br minus. And so really it's kind of like a moot point to even consider H plus going back to Br minus. And also HBr is a strong acid. And so since HBr is a strong acid, then that tells us that the forward reaction, the production of H plus and Br minus, is much more preferred rather than the reverse reaction. So that just leaves us with two options. Option 1, which is H plus reacting with HA. Option 2, H plus reacting with a conjugate base. And so just looking at, the charges, plus is going to go with a minus. So we have this acid that's going to react with the conjugate base. So remember, the conjugate base is A minus. And so when those two react, what happens is that the A minus is going to absorb this H plus so that you get HA. And remember, HA represents the weak acid in this scenario. And so, quick chemistry joke, this solution is laughing at you. Hopefully you guys got that. All right, moving forward. And so looking at our result, do you think the pH will change? And so if you guys recall, the only way that the pH or pOH will change is if the actual number of hydroxide ions or hydrogen ions increased or decreased. So if you guys compare the final state to the initial state, okay, so I'm going to erase this arrow over here. So notice that we have 0 H pluses, we have 0 OH minuses present in the initial state. Here, if you look at the final state, we have 0 H pluses that's floating on its own, and we have 0 OH minus that's floating on its own. And so since we have no H pluses or OH minuses before and after we added that acid, that HCl, then we can conclude that there is no change in pH. And therefore, the pH value in the initial state and the final state will remain the same. And so it's kind of like magic, right? The fact that we added an acid, yet at the very end, after the reaction is done, no acid, no H pluses was present in solution. And so this HA is not H plus. And so since they're not the same compound, then there's no way that this HA can change the pH, just for the sake of this diagram, right? Just the concept, right? Okay. And so, long story short, the addition of that acid or the addition of that base is going to be absorbed by either HA or A minus. And this is the reason why it's so important for a buffer to have a weak acid and its conjugate base. So it can both absorb either H plus or OH minus. And so we're going to go ahead and look at this example again. And this time we're going to go ahead and do it with sodium hydroxide, which is a strong base. Now, I guess I should have done this at the very beginning. Let's go ahead and look at the initial state. And so how many H pluses do you see in this diagram? This diagram that's on the left. Okay, so you see no hydrogen ions. You don't see any H pluses floating. How many OH minuses do you guys see in this diagram? And so nothing, right? We only see HA and A minus. And so if we add a strong base to this solution, what we're going to get is sodium that's floating around and OH minus that's also floating around. And so this is like the initial onset, right? But we're not looking at the initial change, we're looking at the equilibrium. And so once this system has reached equilibrium, or the final state, will this OH minus still be present in our equilibrium or final state? Okay. And so remember that OH minus acts as a base. And this base will always want to react with anything that's acidic, whether it's a strong acid or a weak acid. And so in this system, the only acid that we have is HA. And so it's going to react with one of the weak acids, producing H2O. So this hydrogen, since it's now kind of connected to this OH minus, that's going to produce H2O. And then we're going to get A minus. And A minus is the conjugate base. Okay. So in that final state, the result that we get is water and an A minus. Oops. Yeah, that's right. Okay. And so this HA was consumed to produce A minus. And so let's look at the concentration of H plus and the concentration of OH minus. And so do we see any H pluses floating around in this diagram? No. Do we see any OH minuses floating around in this final state? No. And so therefore, we can go ahead and conclude that since there's no change in the concentration of H plus and OH minus, that there should be no change in the pH, even though we added a strong base to the solution, right? It's crazy, it's magic, right? We added a strong base, and we know that a strong base will increase the pH, yet it won't increase the final result shows that there is no change in pH. Because it didn't change the number of hydroxide or hydrogen ions that's present in solution. Okay. What happened was that strong base reacted with a weak acid, and it was neutralized to form water and the conjugate base. Okay. And so this is how buffers work on an atomic scale, or molecular scale, if you will. Okay. All right, so hopefully through this example, through these two diagrams, you guys are able to understand how a buffer resists changes to pH. Now, I need you guys to also understand that buffers, they don't have this infinite capacity to resist changes in pH. And so each solution, each buffer solution, has a specific concentration of HA and A minus. So they have a fixed, if you don't add any more buffers inside your solution, there's a fixed concentration of HA and A minus, whatever that concentration is. And so if you keep on adding acids or bases, okay, at some point in time, one of these conjugates will be completely consumed if you add enough H pluses or enough OH minuses. In other words, you're going to overwhelm this buffer solution. And when you overwhelm this buffer solution, at some point in time, it's going to consume one of these conjugates. And when one of the conjugates is consumed, for example, HA was completely consumed by OH minus. Now, if you add even more OH minus and there's no more there's no more HA present in solution, then the buffer system will fail, such that there will be a change in, there's going to be a huge change in pH units when you add more hydroxide. So overall, what I'm trying to get at is the capacity of the buffer, or the buffer capacity. And so the buffer capacity represents the moles of strong acid or strong base that will cause the pH of 1 liter of the buffer to change its pH by 1 unit. So that's the minimum requirement. And so if you are adding in like 3 moles of HCl, no pH has, the pH of the solution slightly changed, but it's not 1 pH unit. Then let's just say you added 10 moles of that strong acid. That's actually a lot. Whatever. So 10 moles of that strong acid. And then all of a sudden you see a huge change in pH unit. Within those additions of the 10 moles, at some point you've exceeded the capacity of the buffer to resist changes in pH. just because you've ran out, or not so much ran out, but one of the conjugates, whether it's going to be the conjugate acid or the conjugate base, is going to be completely consumed, so that you don't have any more of these items to buffer out future additions of the H plus or the OH minus. Okay. And so that's the idea of buffer capacity. And logically, if you add more weak acid and its conjugate, or weak base and its conjugate, it increases your buffer capacity. And so if you add only, if you have 1 mole of weak acid and conjugate base, it has a lower buffer capacity compared to, for example, adding 5 moles of the weak acid and 5 moles of its conjugate base. And so the more concentrated your buffer is, its ability to resist changes to pH increases, because there's more of those substances. All right, so that's pretty much it for this lecture. In the next set of lectures, we're going to learn how to quantify, or we're going to talk about calculations involving buffers. All right, catch you guys later. Bye.